Hey, everybody. I'm really glad to be here. This is my first PyBay, actually. Thanks. And I'm going to tell you about the new Python library, and specifically a notebook widget for visualizing large network graphs and AI embeddings. And I want to tell you a little bit about the history of the library, the key innovation behind it, and how it all started. And I would like to mention that everything you see today is an effort of a small team with no external funding, so it's kind of our passion project. Well, as you already know, I'm Nikita. I'm building data tools for more than 10 years already, and I actually have a confession to make. I'm not a Python engineer. I have a background in atmospheric physics. I was doing atmospheric retrievals from sun spectra, meaning the composition of the atmosphere. So I'm a former scientist, but I have never really been a Python developer. At the same time, I spent most of my career working with data and visualizing data, which actually means that I'm a web engineer, because all of the modern visualization tools are web-based. Here, you can see a brief list of my initiatives and projects that I'm proud of. Feel free to check them out, ask questions later. I'm always happy to talk about them. So what is Cosmograph and cosmos.gl? Cosmograph is a library and a Python widget. But first, since every widget that does visualization relies on web technologies, so Cosmograph is a web library. It's also a web tool that allows you to work with large graph datasets. And by graphs, in this context, I mean specifically network graphs and also scatter plots, like the ones you use to visualize machine learning embeddings nowadays. And Cosmograph is powered by DuckDB. And we actually run a WebAssembly version in the browser, and we use it as an in-memory data backend. And we do that because on the web, you often face with out-of-memory issues, and using tools like DuckDB, to some extent, allows you to solve those problems. And on top of that, you can run SQL queries, which is really handy for analytics. Let's answer this question first. Why are people even interested in visualizing network graphs? And everybody might have their own answer, but my interest has two sides. One, of course, is the analytical side. Visualizing graphs makes topology tangible, relationships suddenly become visible, visual layout triggers questions you would never ask from raw data. Also, non-experts grasp visuals intuitively and instantly, which is very convenient. So I believe that it's crucial to draw your data before diving into analysis. But my other interest is actually a creative interest, because graphs are often very beautiful objects. So it's a pleasure to work with graphs because they give you this beauty. There are many graph visualization tools for Python and for JavaScript. And many of them are quite good. But there is one persistent problem: performance. When you try to explore large graphs, all of the available solutions, they become kind of sluggish. So what you see here is a Sigma.js, a very popular JavaScript library, which is also available as a Python widget. And this graph only has 7,000 points and 166,000 links. And you can't interact fluently with this graph. And the reason for that is because there are two big problems when visualizing graphs: layout and rendering. The rendering problem has kind of been solved in different tools using technologies like WebGL. So we know how to render things quickly. But the second problem, the layout problem, is a tricky one, because layout algorithms are computationally intensive, and it's difficult to implement them efficiently on the GPU. And the hardest part of that is this many-body aspect of the simulation, making points repel each other. And there are tricks like the Barnes-Hut approximation to speed it up, but a GPU implementation of that is far from straightforward. So our team, when we started working on this, we perceived it as a challenge. We had prior experience implementing particle simulations on CPU and GPU for data visualization purposes and just for fun. So we were curious if we could make it work. So it started as a fun experimental project and eventually became Cosmograph. So we began with this simple particle simulation to test our ideas. What you see here, probably the first week of development, it was buggy but fascinating. Now this is where a creative aspect comes in. Building such systems can be visually hypnotic, so even bugs can look beautiful, and it keeps you motivated to keep building things till they work. I even think sometimes that maybe I want to go back in my commit history and find this broken version and make like a side project out of it, just like an artistic exploration. And as you can imagine, since I'm giving this talk, the outcome was quite successful. A Cosmograph solves both of the mentioned problems. It runs a WebGL force graph simulation on your machine. Everything happens locally. We don't use any server-side backend. We don't use CUDA. It all runs in WebGL on your computer. WebGL is a computer graphics framework. And we use this trick where we encode the data in textures. And we run algorithm in shaders. So if you don't know what a shader is a program that runs on GPU cores in parallel. And this whole system was initially created for computer graphics. But there are creative ways to use that technology for computations. There are modern technologies like WebGPU, where you have a new type of shaders called compute shaders. They were designed specifically for computations. So you don't need to do all these hacks, but WebGPU is still a very new technology and is not supported on many devices. Here you see a comparison of our core rendering framework engine, cosmos.gl, with other popular libraries. Cosmos.gl is completely open source. It's a part of OpenJS Foundation, the same foundation that houses huge projects like Node.js, Express, Electron. So you feel free to use it. And you can see that Cosmos.gl outperforms all of these libraries by a large margin. It stays smooth even as graph size increases beyond hundreds of thousands of points and links. The largest graph I tried myself had like slightly more than 1 million nodes and few million links. But just recently on our community Discord, somebody wrote that they were able to visualize a graph that has 5 million nodes. And again, it's all just on client-side hardware. So let me dive in a little bit into the technology and tell you about the simulation itself. So you have this force layout algorithm that essentially a simulation where you have multiple forces. So first, this many-body force, which is the hardest part computationally, and this is our key innovation. So I will explain the key trick in a second. Then you have this link force, which is essentially, they're like springs between 2 points. They're either being attracted or repelled from each other. Then you have gravity force that pulls everything towards the center of the graph. You have the centering force that just centers the graph in the viewport. And then we have this new clustering force that we have recently added. You can define a cluster for a set of points. And then on the fly, we calculate the center of mass of all these points, and they all being kind of like attracted towards the center of mass. So let's go a little bit more technical into this many-body force. So if you implement it in a straightforward manner, it has quadratic complexity because you need every point interact with every other point in the graph. And as I mentioned, there are ways to speed it up, but they're tricky to build on the GPU. But we were able to implement what's called a multi-level grid approximation with this idea that short-range interactions are computed directly between nearby particles on the grid, but long-range interactions are approximated collectively using coarser grids where a fine spatial detail is not necessary. So it's like replacing a bunch of remote points with a single larger point. And every grid cell or a pixel, because we use textures, contains information about the center of mass of all the particles within this simulation space that ended up being in this grid cell, and also the number of points. And then we calculate the simplified many-body force. Instead of calculating repulsion with every other point for a given point, we just use a simplified grid, which speeds up the computation 100 times. And it turned out that Cosmograph also a great point cloud rendering tool. So whenever we work with scatter plots, like machine learning embeddings, and you don't need a simulation, you can still use Cosmograph to visualize your point clouds that have millions of points. Cosmograph can handle it easily. So here what you have is a 3 million point data set of chat messages with different large language models. And you can see that it works in real time really smoothly. I also want to mention that we have this unique point sampling mechanism where we can just get a sample of points in the viewport and render labels for just these points. So we can imagine that rendering labels for all 3 million points would be really slow, but rendering just for a sample works fast and still gives you this nice view of the graph where you can see things, see the labels. Another example of an embedding, here you have 350,000 most cited scientific articles. And same idea, so you have paper abstracts, you go through LLM embeddings, and then you project those embeddings onto 2 dimensions using UMAP, and you render that as a beautiful point cloud. So whenever you have these problems, either large-scale graph visualizations, and you need to quickly visualize a graph in Python or on the web, or embeddings, you can use Cosmograph, and it's very easy to use. So you can just do pip install Cosmograph and get your data and get it visualized. So now I want to give you a quick live coding demo. Who doesn't like live coding when things can go wrong? So let's do it. Let me change to mirroring my screen here. Change. This one. Oh, good. So first of all, you can go to PyBay, search Cosmograph, find the package. Very easy to install, very easy to use. We have plenty of examples. Yeah. And once you have it installed, so one thing I have to tell you. I'm going to use just Jupyter Notebook here, not VS Code, for one particular reason. We recently found that the latest versions of VS Code, they easily go out of memory when you work with big data sets, when you try to visualize big data sets specifically, because it runs its own JavaScript instance, and somehow it limits the memory. So here I want to show you that you can work with really big graphs. So I use a Jupyter Notebook, but you can still use it in tools like Colab and VS Code. So just if you see something doesn't work, try it in a Jupyter Notebook. Okay, so here I already imported pandas, I imported Cosmograph, and I have this data set of scientific articles that has data about publications and citations between them. So I'm going to just import that data. So I have my link, have my links. Let me zoom in a little, right? Is it good? Yeah. Do my links, and I read my Procare file. Yes. Links. Okay. And let's see what's in it. Links. Head. Okay, so we have this file with links, just publications IDs, source and target, and the date of the citation. Now, just with this, I want to do Cosmograph. I create a new cell, and I do graph, CG Cosmo, and then I specify my configuration. I want to do links equals links, source, link, source. So I mentioned that we use DuckDB as the backend. So we kind of operate with this idea that you have columns in your database. So we do this by suffix to give user this idea that it's a column in either in your data frame or in a database. So here we do, I'm just going to copy and paste it. Source column, and then target column. What's wrong? This one. Okay, and I don't want to render everything. First, I'm going to just do a subset just in case, just a tiny bit of this data. Let's just 1 million links. So this data set has around 7 million links. Just do 1 million, and does it look good? Okay, let's try. Oh, this Cosmo. And, oh no. Oh no. Just worked. Run again, run again. Okay. Let's save it and try to come back. Oh, this one. This one. Run. Oh, thank you so much. I'm nervous. Yeah. Graph. Yes. Yay. So, and yeah, just in a matter of seconds, you have this beautiful graph that has 1 million links. A lot of links. Thank you. So, and here you can go to the configuration panel, you can change the particle size, you can change the forces that I have just mentioned. So if I click run here, then I can do all of this kind of like simulation tricks in the browser in real time. And what I have here is a M1 Pro laptop, 5-year-old laptop, and it still works great. So let's go even further and bring in points. So we have our point data set. I have 11 minutes left. Points. And we just read another Parquet file. So let's do the same. Points. And so here, we're going to have much more data. Every article has its title, journal, publication date, number of citations, topic, subfield, field, domain, so a lot of metadata, which is nice. And I want to render everything. I want to render points, I want to render links. So if you don't have points data, you can just, like, the Cosmograph creates points from your links data, but you can also provide all this extra support metadata and do things like unique coloring, sizes, everything. Well, let me just show you. So first, I want to render everything, all 7 million links. And I actually want to hide the links because rendering links is slow. So I'm going to do render links false. I'm going to provide my points. And I want to say point color by to be maybe by domain. Then we do point size by, let's do number of citations. Then let's do point cluster. So remember I mentioned the clustering force. Cluster by, we're gonna do subfield. What else? Oh, let's do the timeline. Point timeline by, and let's do the pub date. Okay. Now I'm going to press run, and It will take a few seconds, because when you do this, first you need to get your data, transform it to an arrow, and send from the Python server side to the in-browser framework using arrow. So it takes a few seconds to load, but it's still way faster than using any other graph visualization tool. And okay, here, almost there. Here we go. We have this huge graph. I think it's about 500,000 points, and again, 7 million links. And oh, I didn't do the labels. Let's do the labels. Let's do point labels, label by title. Okay, let's do it again. Yeah. So essentially, I want to emphasize it again, because everything here happens on your own machine. You don't need any server, any other technology. It's all browser-based. And just in a few seconds, I will tell you how you can also share it with the others using your browser. So, okay, here we have our simulation going. Let me hide the points just from now, hide the labels. Yeah, so here you have this massive graph, and you can do things like select a range on the timeline and only see the points from that specific time period. Or I can select a bunch of points like this and access those points from the graph like this. So I do graph selected point indices. It's going to give me the indices of all these points. Then I can do points, and it's going to give me this subset of this data. And I can later on do something else with it. I can also change things on the fly. Like, let's say, so first I specified here that I want my cluster to be by subfield. But what if I want to change it? So I can do graph. I can do point cluster by, and I want to do it just by domain. So let me reset this, start on this. And you will see the simulation will adapt in real time. So you can see the forces has changed. And now instead of having this fine structure of individual smaller clusters, they just form this huge four clusters. So we have 4 domains of science. Yeah. And I also have another example I want to share you. So this is a similar data set, also same data, publications, but this is this semantic map where we have X and Y coordinates. So here, I already ran all these cells. So I have my map right here. But what if I want to show this project to somebody else? So we have this web version of Cosmograph where you can go, you can get your API key, and you can export your project right from Python. Let's give it a try. So if I run this, and I run this, then what's going to happen, it will upload your data and also upload your project and give you a link to the project. Sometimes it's fast, sometimes it takes a while. It's still in progress project, so we kind of tweaking things as we go. And what I'm showing you now today, I have never shown this to anyone before. So this is all very new. And here you have your unique link. So you click on that, and it's going to open a web page for the Cosmograph web tool, where you're going to see the same data, but full screen, where you can do some other things. So here we go. Same data set, timeline. Then you can also do things like search. So you can search for different points. You can do filters, you can add a filter, you can maybe, I don't know, filter by number of citations. And the most interesting thing here is you can click share and publish your project, and it's going to give you a public URL you can just copy and send to anyone. And so we're doing kind of like a soft launch today. So I mentioned that you're the first people who sees it online. So if you go to our hidden website called, the URL is next.cosmograph.app. So here you will see everything, the new app, the widget, everything can do. You can give it a try. You can join our Discord and ask questions. You can ask questions on GitHub. Yeah. This is it. Thank you so much.
We have time for like 1 or 2 questions if people have them.
So I saw you pushed that to the Cosmos app. Is this an open source project? Like, could we run our own Cosmos server?
So the core library called cosmos.gl is completely open source. Then the widget is also open source, so you can use it for data analytics, for everything. But the Cosmograph library is not open source. It's free to use for any non-commercial, educational, all sorts of projects like this. But if you want to use it commercially for a product, then it's something we license out.
Great talk. Can you talk a little bit more about using DuckDB for the backing store?
Sorry, can you say it again?
Using DuckDB for the storage.
Yeah. Well, what specifically? Just why we decided to use it?
Was this performance reasons? Did you look at other options?
Well, it gives a lot of flexibility. So you can do a lot of analytical operations because it's SQL. And then we have this cross-filtering feature, which heavily relies on DuckDB. So you can apply many, many filters really quickly, filter out the graph. Before, we used just objects in JavaScript. They're really heavy. It was a bad idea. So we were trying to open bigger graphs. They're going out of memory. So we tried to find other technologies. We had to rewrite the core engine just to use instant arrays. Works great, very non-user-friendly. And DuckDB, because it's a WebAssembly thing, it has its own memory limit. And there are still some problems, like if you come with a huge data set that is, I don't know, 1 gigabyte, and usually you start having problems when you have textual data. If you have long texts, then it might not fit into the browser memory. But if you don't, then you can open really big networks, like, I don't know, millions of points, and it's going to be fast.